in the last class we showed that the impulse function I, which was defined as P plus rho u square multiplied by the cross sectional area of the stream tube at that location, can be used to calculate the thrust that is produced, thrust or drag that we get from different components, and the thrust could be evaluated as I2 minus I1, where the state point 2 refers to the exit exit of the device and state point 1 refers to the inlet of the device. So, if you look at a conversion nozzle, for example, let us say this is state 1 and this is state 2, then the net force acting on the nozzle can be evaluated by subtract I1 from I2. Okay. Now, when we do this, in this particular case, we do not know whether the nozzle is going to produce thrust or whether the force is going to be in the opposite direction. We can determine this, for example, by using the fact that thrust is also equal to, we showed yesterday that thrust T should also be equal to integral 1 to 2 P dA, with the x component being taken into being calculated for evaluating the thrust. So, when you do this, if you look at this kind of a device, as the fluid flows through, notice that the pressure forces are acting normal to the surface. So, the pressure forces would act like this, on both surfaces. Remember, this is actually the pressure force exerted on the walls, right. So, that is it is very important to remember that, and the pressure force also decreases, I am sorry, the pressure decreases as we go along the length of the nozzle, because the flow undergoes an expansion process. So, if you take the x component of the pressure force on the top and the bottom side, you will then realize that in this case the net force that is exerted on the nozzle is in the positive x direction, which means this is actually a drag force and not a thrust force. So, even if you evaluate I2 minus I1, you should get the same thing. This is what we showed yesterday when we showed the breakup of the thrust produced by different components of an aircraft engine. Positive thrust was generated in the intake, compressor, diffuser and the combustor, and the thrust that was produced in the turbine and nozzle was actually negative, meaning that, indicating that this was a drag force. Okay. However, if you take an entire aircraft engine and evaluate I at the exit of the engine minus I at the inlet of the engine, you will still produce positive thrust, otherwise the aircraft will not fly. Okay. If you take the nozzle alone and look at the forces, net force exerted here, then this is the way it will be. Okay. So, it is important to realize that. However, we need the nozzle because we want to convert the enthalpy of the gas to kinetic energy. So, that is still required. So, we cannot, just because the forces acting on the nozzle are in this direction, we cannot dispense with the nozzle. Nozzle is still required, but the calculation of the thrust or net force acting on a component must be done as impulse function at the exit minus impulse function at the outlet. Or if you know the pressure, it should be the integral of P dA with the appropriate component being evaluated. Okay? Yes?
So, if solid rocket is having only conversion nozzle, then it won't be able to produce thrust?
It won't be able to produce thrust, correct. Okay. The solid rocket will not have a conversion nozzle part alone, because the stagnation pressure in a solid rocket motor, in a rocket engine, stagnation pressure is very high. So, a conversion nozzle will not be enough to actually
like Quasi rocket and all that small stuff, toy rockets,
right.
If they are having only conversion nozzle.
In fact, they are designed slightly differently with enough surfaces to get an upward force on the rockets. If you look inside, you will see that they have enough things to propel them upwards. Okay. We will take a closer look and at this expression and evaluate this for an aircraft engine when we start discussing aircraft engine. That is the next module of the course. We will rewrite this expression for an aircraft engine where some simplifications can be made. But what you must remember is that the pressure force, this is the internal pressure force that acts on the device. There is also an ambient pressure force which is exerted on the outside. So the net force is the difference between the two. So if I show the ambient force like this, the ambient force is a constant value, right. So the ambient pressure force acts like this. So the net pressure force on the surface of the nozzle is this pressure minus this pressure multiplied by the area. So it is advantageous to actually evaluate this pressure with reference to the ambient pressure at that location, so that I need not worry about this and just take this minus this multiplied by the area, and that is an idea that we will use later on when we derive the expression for the thrust of an aircraft engine. Okay, measuring the static pressure with reference to the local ambient pressure and not the sea level ambient pressure. The next topic that we are going to take up is area velocity relationship, which is a very important relation when dealing with flow through varying area passages. So here we try to determine the relationship between changes in velocity and changes in cross sectional area. So what happens when the cross sectional area decreases, or what happens when the cross sectional area increases? That is what we are going to try to figure out. So we start with the differential form of the continuity equation, which can be written like this. And the differential form of the momentum equation can also be written like this: dP plus rho u du equal to 0. Notice that the differential form of the continuity equation does not contain a term which is the integral of the pressure force on the walls, because that is a very small quantity. So if you think about let's say a nozzle like this, right? Let's say that this is my differential control volume for which I am trying to write the momentum equation. So I have pressure force which is acting in this direction, and P plus dP times dA, A plus dA, which is acting in this direction. There is a change of momentum. Notice that this is very small. So the integral of the pressure force on this wall will be 0, because I am integrating over an incremental distance and trying to evaluate an integral over an incremental distance, which means it is equal to 0. That is why the integral term is not present in the differential form of the governing equation. Whereas if I apply it between inlet and outlet, if the control volume goes from inlet to outlet, then I need to account for the net pressure force that acts on the surface. Okay, that is a very important distinction to keep in mind. And the differential form of the energy equation looks like this. So if I take this equation and differentiate things through, then I get the following: UA times d rho plus rho A times du plus rho u times dA equal to 0. And if I divide through by rho UA, then I can get this to be d rho over rho plus du over u plus dA over A equal to 0. Now we are looking for an area velocity relationship, which means the relationship must contain only changes in area, changes in velocity, and area and velocity. So that means I would like to eliminate d rho over rho in favor of du over u. That is what we are going to do next. So we will eliminate since we have assumed the flow to be isentropic, I can write from my entropy equation, which says entropy is constant, I can write this as Tv to the power gamma minus 1 is equal to T0 V0 to the power gamma minus 1, where T0 and V0 are the stagnation quantities. Or if I rewrite this in terms of density, I can actually write this as T to the power 1 over gamma minus 1 divided by rho is equal to T0 to the power 1 over gamma minus 1 divided by rho 0. And if I differentiate this expression, I get d rho over rho is equal to 1 over gamma minus 1 times dt over t. So, we wanted to write d rho over rho in terms of du over u. We have managed to write d rho over rho in terms of dt over t. Now, we have to relate dt over t to du over u. Changes in static temperature have to be related to changes in velocity. How do we do that? We use the definition of the stagnation temperature and the fact that stagnation temperature is a constant, right. So, we can write so we eliminate dt over t in favor of du over u. Since the stagnation temperature is T naught equal to T plus u square over 2 Cp, and that is a constant because the flow is isentropic, there is no heat addition or work addition, right. So, this is constant. So, if I take the differential on both sides, I get dt equal to minus 2u du over 2 Cp or I can also write this as dt equal to Cp is gamma r over gamma minus 1. So, I can write this as gamma minus 1 over gamma r, and if I multiply and divide by a u, I get this to be u square times du over u. And if I use the fact that u is m times square root of gamma RT, I can write this as gamma minus 1 over gamma r times u square then becomes m square times gamma RT du over u. So, the gamma r cancels out and I end up with an expression where I have dt over t is equal to, I am sorry, I missed out a negative sign here. So, there should be a negative sign here and there should be a negative sign here. So, dt over t is equal to minus gamma minus 1 times m square times du over u. So, I finally have what I was looking for. I wanted to eliminate d rho over rho in favor of du over u. So, here I expressed d rho over rho in terms of dt over t, and then I have now eliminated dt over t in terms of du over u, so that I finally end up with an expression where I can say d rho over rho. So, therefore, d rho over rho is equal to 1 over gamma minus 1 times dt over t, but dt over t itself is equal to gamma minus 1 m square times du over u. So, I am going to write this as gamma minus 1 times m square times du over u. So, we can say that d rho over rho is equal to minus m square times du over u. So, if I substitute the expression for d rho over rho, if you remember, d rho over rho is written in terms of du over u here, and if I substitute this into my differential form of the continuity equation here, I finally get a relationship which involves only dA and du, which is what I am looking for in my area velocity relationship. So let us go ahead and do that. So if I do this, I end up with the following expression: dA over A is equal to m square minus 1 times du over u. So this is the so called area velocity relationship, okay, where changes in velocity are related to changes in the cross sectional area of the passage. Now with this we can get an idea of what changes in cross sectional area of passage does to velocity. Does it increase or decrease the velocity? That will depend upon whether the flow is subsonic or supersonic, because the Mach number is also involved in this expression. Okay, let us take a look at that next. So we are going to actually do the same thing that we did earlier. We will tabulate the changes in the same manner as we did earlier. If you remember, for Rayleigh flow and Fano flow we did the same thing: m less than 1, m greater than 1, and there are two possibilities: dA greater than 0, which means that A increases, and dA less than 0, which means that A decreases. So when the cross sectional area increases, dA greater than 0 for a subsonic flow, this term is negative. When dA is positive, right, then du becomes negative, right. So a subsonic flow in a diverging passage decelerates, right. So u is negative, or if I write this symbolically as we have always done, we can write it like this: u decreases. Similarly, if dA is negative, this term is also negative for a subsonic flow, so du becomes positive, so u increases in a converging passage for a subsonic flow. And I can show easily that u for a supersonic flow, u increases in a diverging passage and u decreases in a converging passage. So this tells me that subsonic flow decelerates in a diverging passage and accelerates in a converging passage, and supersonic flow accelerates in a diverging passage and decelerates in a converging passage. We can also interpret this slightly differently by using our earlier two equations, where we have written down d rho over rho in terms of du over u and the differential form of the continuity equation. Okay. The argument goes like this: let us say that we are looking at a subsonic flow. At one point, let us say that the velocity increases slightly, right. Let us say du is positive. That means d rho over rho is negative, and since m is also less than 1, the magnitude of the quantity is also less than du over u. It is negative, but the magnitude is also less than du over u, right. So now if I use that information in my continuity equation for mass conservation, this sum must always be equal to 0. So this has increased slightly because I said du was positive. Now this has become negative but less than this. That means for this entire equation, left hand side to sum to 0, what should dA be? dA should be negative, right. So it is as if this is 10, this is minus 8. So this has to be minus 2 to make the whole thing go to 0, which means that dA has to be negative. So, if du is positive and the flow is subsonic, then dA has to be negative in order to satisfy mass conservation. On the other hand, if let us say the flow is supersonic and the velocity increases slightly, du is positive, then d rho over rho is actually negative and greater than du over u, right. So, when I look at mass conservation now, what happens is, this was, we said was 10, now instead of this being minus 8, this has become, let us say, minus 12, then this would have to be plus 2 to make the whole thing go to 0. So, that means dA has to be positive. So, the change in behavior when the flow is subsonic to when the flow is supersonic comes because of the Mach number dependence of the change in density. What this tells me is that for the same change in velocity, for the same value of du, the change in density is less in the case of subsonic flow and more in the case of supersonic flow. And if you remember in our very first lecture, when we drew lines of V equal to constant on a TS diagram, we said that the lines are spaced closely for lower temperatures and spaced farther apart for higher temperature. Now, that is what is causing this effect. So, the same change in du, right, results in larger change in density if the flow is supersonic and smaller change in density if the flow is subsonic, and that is what is causing the flow to behave differently, exactly opposite, depending upon whether it is subsonic or supersonic. Okay. So, change in density for a given change in velocity is much more when the flow is moving at supersonic speed and much less when it is moving at subsonic speeds. Okay. So, that is an extremely important conclusion that comes out of this equation. Okay. Now, notice that there are actually three possibilities in this equation for dA. We have looked at dA positive, dA negative, but we have not looked at dA equal to 0, right. That is also a possibility which we must entertain, and that brings us to the next topic, which is we have looked at thermal choking, where enough heat addition could cause the Mach number could go to 1, either from a subsonic Mach number or a supersonic Mach number. With enough heat addition, we can make the Mach number go to 1 or the flow attain sonic state. We saw with friction also that if you make the pipe long enough, we can attain the sonic state in the pipe if you make it long enough. Now, so that was friction choking. Now we are looking at geometric choking, that with the geometry being designed in a certain way, we can attain the sonic state once again in this flow also. That is what we are going to discuss next. Now, from this relationship, as m goes to 1, you can see that dA goes to 0, right, very simple. So, this means that what does this mean? Does this mean that wherever dA is 0, we attain m equal to 1? Not so fast, right. We need to look at different possibilities to see what kind of solutions are allowed. Let us look at two scenarios where dA is equal to 0, and then we will see whether m can become equal to 1 in both these cases. The first scenario is a passage that looks like this. Right. So, at this location dA is equal to 0, and we look at another scenario where the passage is inverted inside out, right, inside out of the same thing. So, the passage looks something like this, and you see that here dA is 0. So, now whether we have to see whether m equal to 1 can be attained in these two situations. Let us say that we start with this with the first case. Let us initially say that m is less than 1. So, the flow enters this passage with the subsonic Mach number, and then what will happen to the Mach number as it goes through a converging passage? The Mach number increases, the flow accelerates, is a subsonic flow. So, it is possible for me to accelerate to m equal to 1 here, and then from here onwards the flow will decelerate perhaps or accelerate depending upon the back pressure conditions. It will decelerate or accelerate, but it is possible for me to have m equal to 1 here. Okay, do you understand that? So it is possible to achieve if it is subsonic. What if the flow is supersonic? Right? If I say that the incoming flow is supersonic, let us say m greater than 1. If it is a supersonic flow, it enters a converging passage, what happens to the flow? The flow decelerates. So that means m decreases. So it is possible for me to decelerate from the supersonic Mach number to m equal to 1. So both cases, irrespective of whether it is subsonic or supersonic, it is possible to achieve m equal to 1 at this location where dA is equal to 0. Now if you look at this case, let us say the flow enters with a subsonic Mach number. Okay, let me just add an arrow here to show the direction of flow. So let us say that the flow enters with a subsonic Mach number, and then in the subsonic flow, what happens to the subsonic flow in a diverging passage? The flow decelerates. So there is no way I can actually attain m equal to 1 at dA equal to 0 because the Mach number is decreasing. So attaining m equal to 1 at this dA is not possible in this case. Similarly, if the flow enters with the supersonic Mach number, then the flow accelerates in the diverging passage, so I cannot attain m equal to 1 in the supersonic case also. So which means that in this case, although dA is 0, m equal to 1 is not possible. So dA may be 0, but m equal to 1 is not possible. Okay. So what this tries to tell me is that if m equal to 1 occurs, then it can occur, it is not sufficient if you have dA equal to 0. This also says that it must be a point of minimum cross sectional area. dA can be 0 for minimum as well as maximum cross sectional area. So what this tells me is if m equal to 1 occurs, then it must occur at a point of minimum cross sectional area, and such a location, point of minimum cross sectional area, is usually called a throat. Now this relationship, there are other aspects to this relationship which we will see next. So we have looked at this situation as m goes to 1, dA goes to 0, right? As m goes to 1, dA goes to 0. That is okay. Now what about the converse? Okay, so if you look at this equation, we have seen that as m goes to 1, dA has to go to 0. The converse is if dA goes to 0, what can we say about m? The left hand side of this equation, if it tends to 0, what can we say about the right hand side? Does m have to go to 1? That is not necessary because the right hand side has two terms. So if the left hand side goes to 0, either this can go to 0 or it is possible that this can go to 0, in which case m can be anything, it need not go to 1. So the converse is not always true. If m equal to 1 occurs, it must occur at the throat, but just because you have a throat does not mean that m should always be 1 there. Okay, that is a very important point. So as dA goes to 0, we can then write either m tends to 1 or du can go to 0. which one we actually see in practice depends upon the conditions that you are maintaining in the flow situation, the downstream pressure, the upstream stagnation pressure, stagnation condition, and so on. It depends upon the actual situation. So, depending upon the situation, either m will tend to 1 or du will go to 0. If du goes to 0, then m can have any value. Okay. So, we can sum up these two as follows. If m goes to 1, it can go to 1 only at a throat, but just because there is a throat, m does not have to be 1 there. Okay. Remember, this is an extremely important point in gas dynamics. If m is equal to 1, but m need not always be 1 at the throat. So, a good example is given right here. We showed that m cannot be equal to 1 in this case, but the flow can come in with some Mach number. If it is supersonic, it will accelerate, reach a higher Mach number. For example, it can enter at 2, maybe reach 2.5 and then decelerate here and exit at 2 or 1.8 or whatever it wants, which is perfectly okay. Similarly, in this case also, it can enter at some Mach number, let us say supersonic, decelerate. So, it starts from 2, let us say it decelerates to 1.5 and then it can again accelerate and exit at Mach number, let us say 3, that is allowed. Or it can come at Mach number 0.4, accelerate to Mach number 0.8 and leave with Mach number maybe 0.3 or 0.5, 0.6, whatever. So, m need not always be 1 here. Whether you get m equal to 1 here or not depends upon the actual flow conditions, the upstream stagnation conditions and the pressure that you are trying to maintain downstream. It will depend on many things. Okay. Because m reaches 1, because it is possible to attain the sonic state here, we call this, if sonic state is attained, we call this geometric choking. Okay. But the important point is we need not actually see a sonic state here, just like what we did with Rayleigh flow and Fano flow. The sonic state need not occur, but we can extend the situation and assume that a sonic state occurs and then relate flow properties to the sonic state, because the sonic state is a very convenient state since m is always known there, m is always 1 at the sonic state. So, I can always imagine a situation where m becomes equal to 1. Okay. If for example, in this flow situation m does not become equal to 1 here, then I can conceive a flow situation just like what I did for Rayleigh flow and Fano flow. I can extend this and for example, do something like this, where the sonic state, I ensure that for the conditions the sonic state is reached here. Then I can relate flow properties at any one of this section to the flow property at the sonic throat, just like we did for Rayleigh flow and Fano flow, and then proceed with our calculation. Okay, which is what we are going to do next. We are going to derive something called an area Mach number relationship, which will allow us to relate the Mach number at any cross sectional area to the cross sectional area at a sonic state. I have finally learned how to manage this board effectively. The board in the actual classroom is twice this size, but this board I am losing some part here and I am losing some part there, and I cannot use the lower half of the board because it is too low. So I am actually working with 1/4 of the board that I am normally used to working with. So they are raising the bar for me, they are making it very challenging for me to do this, which is good. It is only when you are challenged that you can rise to the occasion. So when I come now, it is not enough if I prepare for the lecture. I have to rehearse the lecture and keep an idea of where I should write everything so that I do not erase too many times and use the same thing over and over again. So I do not prepare, I rehearse, which is good. That I would have never done in my life. Okay, so we are now looking at area Mach number relationship. So the previous one was an area velocity relation. Now we are looking at area Mach number relation, because as you know, once I know the Mach number at a station, all the other quantities, all the other flow properties can be evaluated. So we can derive, if we can derive a relationship involving this, then we are okay. So let us assume that a sonic state occurs somewhere in our flow, and we are looking at a flow with an area, with a passage whose area of cross section varies. So the m dot at any section can be written as rho ua, and assuming that a sonic state exists like I showed in the previous diagram, I can also write this as rho star u star times a star. So if I rearrange this expression, I can write this as a over a star is equal to rho star over rho times u star over u. And I can simplify this as, or rewrite this as rho star over rho naught, where rho naught is the stagnation density, times rho naught over rho star times u star over u. Did I write this correctly? I am sorry, this is rho star over rho, there is no star here. Since the flow is isentropic, rho naught is constant, so that the stagnation density at the point where the sonic state occurs is the same as the stagnation density at any other point in the flow. Otherwise I will not be able to use this. For example, Rayleigh flow or Fano flow, this will also keep changing, because either T naught keeps changing or P naught keeps changing. So this will also keep changing. So rho 0, the stagnation density where the sonic state occurs will be different from the stagnation density at any other state. So I will not be able to make use of this in the other two cases, but here because the flow is isentropic, rho naught is constant, I can write it like this. And if you recall from our first module, rho naught over rho can be written as 1 plus gamma minus 1 over 2 times m square raised to the power 1 over gamma minus 1. And if I substitute m equal to 1 in this relationship, then I get rho naught over rho star as okay. The idea is to write, remember we are looking for a area Mach number relationship, right. So the area is on the left hand side. The idea is to write everything on the right hand side in terms of Mach number and Mach number only, okay. So now I have this in terms of gamma, I have this in terms of my Mach number, I need to rewrite this in terms of Mach number, that is what we are going to do next. So we will write u as being m times square root of gamma RT, and u star, if you remember, u star is the speed of sound, so u star is equal to square root of gamma R T star. So substitute all this into this expression for A over A star, I can write this as A over A star is equal to 1 plus gamma minus 1 over 2 times m square raised to the power 1 over gamma minus 1 times 2 over gamma plus 1 raised to the power 1 over gamma minus 1 times 1 over m times square root of t star over t. So, we are making progress. The only term that is left is this t star over t, but I can write t star and t in terms of t naught and finally do what I have always been wanting to do. So, if you remember, t star is equal to t naught divided by gamma plus 1 over 2. And t is equal to t naught divided by 1 plus gamma minus 1 over 2 times m square. So, substitute everything into this, you end up with an expression that looks like this. This is the so called area Mach number relationship, where we have the area term on the left hand side and the Mach number term on the right hand side. Here A star is the area or cross section where the Mach number reaches 1, and as I said earlier, A star need not be equal to A throat. If the flow is choked, then A star is indeed equal to A throat. Otherwise, we have to determine A star in some other manner. Okay? This kind of situation may arise later on when we look at for example flow through a convergent divergent nozzle. We will look at examples involving this. So, let us say that we have flow through a convergent divergent nozzle. This is the throat. It is quite possible that we have a situation like this: subsonic Mach number at entry, m becomes equal to 1 at the throat, and there is a normal shock that stands somewhere here. So, m accelerates to a supersonic speed and then it becomes subsonic after this. In such a situation, A star for this part of the flow will be equal to A throat, right? A star for this part of the flow is equal to A throat, but A star for this part of the flow field is not equal to A throat. It has to be something else. So, that means we are actually imagining extending this section in such a way that, for example, maybe the A throat or A star for this case, second case, has to be something like this, whereas this is A star is equal to A throat for this case. This need not be the same as this. In fact, this will not be the same as this. Okay, that is what I meant when I said A star need not be equal to A throat. Okay, and different parts of the flow field can have different A stars. Although there is only a single throat, different parts can have different A stars. Now, this equation for a given value of A over A star, notice that for a given value of A over A star, this equation can give you two solutions, one corresponding to a subsonic flow and another corresponding to a supersonic flow. That is also clear if you look at the same flow situation, right. So, for example, if you look at a flow situation like this, where m is equal to 1, and if, for example, the flow enters at a subsonic Mach number and exits with a, let us say, supersonic Mach number, then the A star in this case is equal to A throat, correct? A star in this case is equal to A throat. However, if I consider two sections like this, right, this cross section and this cross section, notice that A by A star for both these cross sections are the same, but here the flow is subsonic, here the flow is supersonic. That is what I meant when I said for a given value of A by A star, I can get two solutions, one corresponding to the subsonic branch and another one corresponding to the supersonic branch. Okay, let us write this down formally. So, m less than 1 is one solution and m greater than 1 is the other solution. Okay. Once again, what we try to do is we do not try to solve this equation for different values of m. We use the same strategy as what we did earlier. We tabulate this function for different values of m. So, I take m equal to 0.1, 0.2, 0.3 all the way up to let us say m equal to 5 and I substitute the value here, I calculate A by A star. So, I make a table. So, whenever I have a given value of A by A star, I go into the table and figure out my m depending upon whether I am looking for the subsonic solution or the supersonic solutions. So, this function is tabulated and we will use this table to do our calculations rather than solving this equation every time. Okay. What we will do in the next class is to look at an expression for the mass flow rate through a choked nozzle, because that is one of the most important expressions that we will encounter in gas dynamics, that has far reaching implications on many equipment handling compressible flow, especially aircraft engines. That is what we will do in the next class.